Hello everybody. In this video, we're gonna talk about the valves in in Aspen Plus. In the previous video, we saw that we can add the minor losses, and we saw that one of the sources of minor losses was the valves. And what we did in the last video is that we added or through the fittings part here, we were able to add the gate valve or the butterfly valve, whatever the type of valve that is available here. We have only two types of valves here, and we saw that we don't have the option of having the percentage of opening of the valve. And to get this problem solved, we said that we can add the miscellaneous K factor, which we can get from the tables or from wherever we source we have information about the valve from. In this video, we'll see more details about the valves, which are not available in the pipes, like what we saw in the previous video, and this is gonna be through this valve button. And in this button, you can see they're all the same, but we have different shapes. I'm just gonna pick this, and let's say I'm gonna connect it here. So this is gonna be the inlet stream, and this is the outlet stream. I'm gonna call it valve to be easy for me to understand that this is the valve. So now what I'm gonna do is to explore what is inside the valve and what's different from what we saw in the previous case in the minor losses in the pipes. So we will see here that we have three modes of calculations. The very first option is the calculation type. You can either do what's called the adiabatic flash for specified outlet pressure, and this is very simple actually. What it does, it just does the flash calculations as if it is a flash drum. You specify what is the outlet pressure or the pressure drop. So for instance, if I mention or want the pressure drop to be 0.5 atmosphere, it's done. There are no more information that it's required from me to define or to provide to the software so that it can do the calculations. I don't have any possibility to do any or put any information here. So the only source or place or piece of information that I want to define when I choose the adiabatic flash is just the pressure drop. And by this I can run the file, and it should be enough for me to get it done. But of course, I would expect that the outlet or the output information that I'm gonna get out of this inputs or using this inputs is gonna be small, because I didn't provide a lot of information, so I don't expect to find a lot of results. And that's why what we see here is just some very basic results. Just the pressure drop is 0.5 atmosphere, the temperature, and the vapor fraction, which is very basic information. So this is not what I am interested in actually. This is it might be useful in some cases, but this is not what I want to focus on in this video. The focus of the video is going to be the two other options, and it's important for me to make sure that you understand the difference between these two, because this is gonna be something that we will see in the next like topics in this series. We will see this in heat exchangers. We will see this in distillation columns. So I believe it's important to understand the difference between the design and the rating modes. So the first option, which is the design mode, is that you, and I think it's clear from the name. It's design, which means that I want to achieve something, and to achieve this thing, I want to design the system to achieve what I want to do. So this is what it does. So it calculates the valve flow coefficient for specified outlet pressure. So I specify the outlet pressure, and it calculates what's called the flow coefficient, which is something that we will talk about in a minute. But let's say this is a parameter that is related to the valve, and it is what I could get out of the of the simulation when I specify the outlet pressure. The rating is the other way. In the rating mode, you specify the parameter of the system, which is going to be the flow coefficient, for instance, and you want the software to tell you what will be the output of the system using these specs, which is the other way. One of them, you specify the output that you want to get, and you want to know what should be the design of the system. And the other way, it is the providing the design, and you want to see what this design would give as an output. So these are two different modes, which is the design and rating. So before going through the details of this part, let's go and understand what are the specs of the valve that we are interested in. So we have like these three parameters, which is the flow coefficient with the symbol CV, the pressure drop ratio, which is the symbol is XT, and the pressure recovery factor, which is FL. To get a feeling or understanding of these parameters, let's understand how the valves work. So we know that the valves, in general, they do some constriction to the flow. You decrease the area of the flow, and this leads to an increase in the velocity, and this leads to a decrease in the pressure, and this is why we get some pressure drop in the pump. I mean in the valve. And this is what we usually get in cases like this. Of course, it's not always this way, but it's gonna be similar in a way or another according to the geometry of the valve. And this is the area which is the minimum area that the flow will pass by, but this is not actually gonna be the minimum area of the flow. So this is the smallest area that you can see. But the flow will, by the inertial forces, will get kind of more narrower after this constriction, and then it expands again and returns back to its original surface area. And this is what we call the Vena contracta. It's very, very famous, and this is kind of the source of the losses that happen in the pipe, in the valves in general. To understand why we have these losses, we can compare this chart to this diagram that we have here. So here we have the pressure, or let's talk about the velocity first. So this is the velocity. We start with this kind of small velocity, and as the diameter decreases, the velocity increases until it reaches the vena contracta, where the velocity is maximum because this is the minimum flow area, and then it returns back to its original velocity because it returns back to its original surface area. So the flow is the flow rate is constant, and then the area is constant here and here, so the velocity should be the same in both cases. But for the pressure, it's kind of different because we start with high pressure, and as the velocity increases, the pressure decreases, so it keeps going down, down, down till it reaches its minimum value at the vena contracta, and then it rises again as the velocity decreases when the area increases. But it does not reach the P1 value as the velocity did. So we have here what we call the pressure losses through the valve. So we have now the P1, which is the inlet pressure. We have here the PVP, which is VC, which is the pressure at the vena contracta, and then P2 is the outlet pressure. We have these three parameters. The first is the flow coefficient. There are many definitions for the flow coefficient, but just to make life easier and to not go into very complex definitions, you can think of the CV or the flow coefficient as a ratio or a relation between the mass flow rate or the volumetric flow rate and the pressure drop. As the CV gets higher for a constant mass flow rate, this means that the pressure drop is lower, which is more favorable. I don't like to have a lot of pressure drop through the valve, so I would prefer the CV to have a high value. And I think this is the simplest way to think about the CV, just a relation between the flow rate and the pressure drop. and it's favorable to be high in value. The pressure drop ratio is the ratio between the pressure drop, which is P1 minus P2, and the initial pressure, which is P1. The pressure recovery factor is it kind of represents how much of the pressure that is lost here is recovered after the vena contracta. So we have here loss in the pressure, and we have here the recovery, as it says here it's a recovery region. So this is the region where the flow regains its pressure when the velocity decreases. So it's calculated from this equation, which is the P1 minus P2 divided by P1 minus PVC under the root. So these are the three parameters. The CV is kind of, we'll talk a little bit more about CV because it's kind of important, and it is related to the percent opening of the valve. So we said before that you can have a valve like, and this is what we saw here in these charts or in these tables, the gate valve, if it's a quarter closed, you'll have a value of the CV or the KL. For half closed, you will have another value. For three quarters, you will have another value. And the ball valve, it's third closed or two-third closed, you will have different values according to the percent opening of the valve. And this is something that has been studied a lot, and there are relations that tells us how the percent opening of the valve relates to the flow rate passing through the valve. So this is the percent of the maximum flow, and this is the percent of rated travel, which is the percent of the opening of the valve. So the valves behave in different ways. Some valves have very quick response. So for small values of the valve opening, you would have very high flow rate. So if it's open for 20%, you would get 40% of the flow flowing through the valve. If you have it open 60%, it will allow 90% of the flow to pass. So it's what we call the quick opening shape. There is a linear shape, there is a modified parabolic shape, and this is the equal percentage. So there are not, I'm not going to go into these details, but these are known equations for the relation between the percent of the maximum flow and the percent opening of the valve. And to be able to predict the value of the CV at different openings, percentage openings, we can use this relation, which is the CV equals the maximum value of the CV multiplied by the f of x, which is one of these relations. If either it's quick opening, if it's linear, if it's modified parabolic, whatever the shape of the relation. So these are the informations, briefly, the information that we need to know so that we can understand the inputs that we are going to give to Aspen Plus. So here we're talking about the design mode, and here I specified that I need a pressure drop of 0.5 atmosphere, but still I need to provide more information about the valve or the valve parameters. So in this part you can you have one of two options. Either to define the type of the valve, which is either ball, butterfly, globe, whatever. And here you should pick something that, or one of the valves that are available in the library of the software. So here you'll find that there is only one manufacturer who is available in the library. I'm just picking any random valves just for the sake of explanation. And here you see that by choosing the valve and the dimensions, the style, the series, it gives us a relation between the percentage opening, the CV, and XT and FL. So I can simply know for each one of these values, or for each percent opening, the values of the CV, XT, and FL that are important for the software to do the calculations of the valve. So if I run the file now, I should get more results than what I got before. So here I got the outlet pressure. In atmosphere it should be 0.5 atmosphere because this is what I specified. It tells me that the outlet temperature and the flow coefficient, which is the CV, and the percent opening. So this valve that I specified should be opened by 30% to achieve 50 or zero point 0.5 atmosphere pressure losses. Um, and these are the pressure drop ratio or factor and the pressure recovery factor. So these are the information that I should get when I use the design mode. Let's say I'm using one valve that is not one of these, or it's not one of the valves that are available in this options. So in this case, I cannot pick this option from here. So I need to find another alternative, and this alternative is using this part in the bottom here. So here it asks me to give the valve characteristics, which are these three pieces of information: the CV, XT, and FL. And it will ask me to provide the shape of the relation so that it can predict the value of CV, the FL, and the XT according to this relation that we're using. So I'm gonna pick any random values. The CV at 100%, I'm gonna pick it as 4. The pressure drop factor, zero point 0.8. I'm just putting any random numbers, 0.65. And now I can run the file or run the simulation and get the results, and you'd see that it is giving again zero point 0.5 atmospheres. And it is mentioning that the valve flow coefficient is 2.936 and the percent opening is 85.7. And these are the values that I provided. So you have the flexibility now in the inputs that you have to either depend on the inputs that are available in the software's library, or to provide the inputs according to what you have or what you know about your valve uh, that you're working with. You can also um, or put the values that you have here in the table. So I can put like in 10% opening, you can provide the values here, and then at 20% you can provide the values here. So you can put the data, this information as tabulated data without defining the valve from the library of the software. So this is kind of briefly the inputs that we need to put and the outputs that we expect in the design mode. We're going to talk about the rating mode in the next video, inshallah. So I'll see you then. Goodbye.